Alright, so in this video I'm gonna be explaining another important article with the title Maximizing Influence with Graph Neural Networks. This paper in 2023 in an international conference on advances in social network analysis and mining. Finding the seed set that maximizes the influence spread over a network is a well-known NP-hard problem. Though a greedy algorithm can provide near-optimal solutions, the sub-problem of influence estimation renders the solutions inefficient. In this work, we propose GLIE, a graph neural network that learns how to estimate the influence spread of the independent cascade. GLIE relies on a theoretical upper bound that is tightened through supervised training. Experiments indicate that it provides accurate influence estimation for real graphs up to 10 times larger than a train set. Subsequently, we incorporate it into influence maximization technique. So we first utilize cost-effective lazy forward optimization, substituting Monte Carlo simulations with GLIE, surpassing the benchmarks albeit with a computational overhead. To improve computational efficiency, we develop a provably submodular influence spread based on GLIE representations to rank nodes while building the seed set adaptively. The proposed algorithms are inductive, meaning they are trained on graphs with less than 300 nodes and up to 5 seeds, and tested on graphs with millions of nodes and up to 200 seeds. So there are many combinatorial problems like traveling salesman that are very hard, computationally very hard. So like influence maximization problem, which is very hard. And the goal is just finding a set of nodes in a network that would maximize number of nodes reaching the starting diffusion from them. And even the influence maximization problem is NP-hard. So it is proven to be NP-hard. From a reduction to the set cover problem. Moreover, the influence estimation problem that is embedded in IM, influence maximization, for example, estimating the number of nodes influenced by a given seed set, is P-hard and would require 2 to the number of edges possible combinations to compute exactly. So we address it using graph neural network to capitalize on the aforementioned advantages and their ability to easily incorporate contextual information such as user profiles and topics. So we introduced GLIE, which is a GNN model that aims to learn how to estimate the influence of seed set S. This is your starting nodes of the diffusion over a graph. So, if A is adjacency, if you remember previous video, similarly we can define these feature nodes. We define it like this. If it is in the seed set, it is 1, otherwise it's not, it's 0. So, for the analysis that follows, we set the dimension equal to 1. More dimensions will become meaningful when we parameterize the problem. So if we normalize it with the row stochastic transition matrix, the degree is just the in degree of a node, and this is the number of set of neighbors of node U. And note that in the case of directed influence graphs, A should correspond to the transpose of adjacency matrix. So this is important. P P of U condition of U on your seed set S resembles the probability of a node U getting influenced if its neighbors belong to the seed set. For example, during the first set of diffusion, and we can use message passing to compute a upper bound of that. So P hat is just an upper bound for P of U condition in S. So I repeat again, the influence probability, this is important, the influence probability of node U condition of seed set S resembles the probability of a node U getting influence of its neighbors belong in the seed set during the first step of diffusion. So we calculate it like this, the upper bound, A times X, where the second equality term stems from the definition of weighted cascade and the inequality from the proof in this reference. So as the diffusion covers more than one hop, the derivation requires repeating the multiplication to approximate the total influence spread. To be specific, computing the influence probability of nodes that are not adjacent to the seed set requires estimating recursively the probability of their neighbors being influenced by the seeds. So if we let H1 to be A times X, and we assume the new sets S to be nodes influenced in the step T minus 1, their probabilities are stored in H sub T, much like a diffusion in discrete time. We can then recompute the new influence probabilities. So the theorem says that this computes an upper bound to the real influence probabilities of each infected node. The proof is very easy. Let's see what this upper bound is. If you multiply A and H, then it can be upper bounded by, the lower bound is P transpose. So it means that P hat is the upper bound. It's very easy to understand. And then, but in reality, due to existence of cycles, two problems arise. Firstly, if the process is repeated, the influence of the original seeds may increase again, which comes in contrast with independent cascade model. This can be controlled by minimizing the repetitions. For example, 4 repetitions cause the original seeds to be able to reinfect other nodes in the network with triangles. To this end, we leverage up to 3 neural network layers. Another problem due to cycles pertains to the probability of neighbors influencing each other. In this case, the product of the complementary probabilities does not factorize for the non-independent neighbors. So the product that represents non-independent probabilities is larger than the product of independent ones. This renders the real influence probability, which is complementary to the product, smaller than what we compute. We can thus contend that the estimation provides an upper bound on the real influence probability, and we can use it to compute an upper bound to real influence spread of a given seed. For example, the total number of nodes influenced by the diffusion. Since message passing can compute inherently an approximation of influence estimation, we can parameterize it to learn a function that tightens this approximation based on supervision. In our neural network architecture, each layer consists of a GNN with batch norm and dropout omitted here, and starting from H0, we have this update. Then the readout function summarizes the graph representations, and finally, you have the output that represents the predicted spread. So this is a visual depiction of the pipeline. The layers are depicted by a heat map of an actual seed during inference time, showing how the values vary through different nodes. So CELEF in 13 is an improved version of the greedy algorithm for influence maximization that exploits the property of submodularity to select seed nodes efficiently. By maintaining a sorted list of nodes based on their influence spread, CELF identifies the best node with the highest marginal gain in each iteration, resulting in significantly faster execution times compared to the greedy algorithm without sacrificing its original effectiveness. So we propose an adaptation where we substitute the original CELEF IE based on MCIC with the output of the GLIE. So these are in Appendix B, Appendix C. For example, here is the PUN baseline, potentially uninfluenced neighbors. And that's it.